About conditional probability last week, and just to remind you about what a conditional probability means, let's think of just an imaginary scenario, and let's look at two parts of the population. Population A will be millionaires, people who have a net worth of over $1 million, and population B will be Powerball winners. Okay? So I'm using this example to illustrate what we mean by conditional probability. This should be natural to think about. So if I'm talking about the probability of A given B, I'm saying what is the probability that someone will be a millionaire if they are a Powerball winner? Yeah, you can let her. What is the probability that someone is a millionaire given that they're a Powerball winner, right? Well, this should be pretty high, right? This should be almost 1. Because unless you have made some very foolish financial decisions, so that's why the garbage can drops. So if you know that someone has won the Powerball, it's pretty likely they've got a lot of money, right? It seems reasonable. So that probability is probably around 1, right? Which is why if you win the Powerball, you should decline to get your picture taken with the big check and be on the news, right? Because then everyone knows you've got a lot of money. That'd be a bad idea. Now, what is the probability that someone is a Powerball winner given that they are a millionaire? What percentage of millionaires do you think are Powerball winners? Basically 0, right? There's not a lot of Powerball winners. There's plenty of millionaires. So this would probably be closer to 0. So the probability of A given B and the probability of B given A are two very different things. Right? These conditional probabilities are different. And if you recall, let me write the formula for finding a probability of A given B. This is the probability of A and B, the intersection of events A and B, divided by the probability of event B. All right, that's the formula we learned on the Friday before spring break. So now let's do some example problems where we take a look at these again. Okay, this problem says 2 playing cards are drawn one after the other from a deck of 52 cards. And we're going to ask, what is the probability that the first card is red and the second card is black? Okay, what is the probability that the first card is red and that the second card is black? Now, roughly, this should be about 1/4. Because the probability that the first card taken is red is equal to 1/2. And then the probability of the second card being black but it's not actually equal to 1/2. It's slightly bigger than 1/2 because we've taken one red card out. So we got to be careful when we compute this. So let me write 2 events here. Event F is going to be the first card is red. And event E is going to be the second card is black. Okay, so what we're trying to find is the probability that the first card is red and the second card is black. So that is the probability of E and F. This is a little bit difficult to compute on its own, but we can use this conditional probability equation to make this one a little bit easier to compute. The probability of both of these things, the first card being red and the second card being black, is going to be equal to the probability that the second card is black, given that the first card is red, times the probability that the first card is red. I have interchanged E with A and F with B in the formula above. I've interchanged E with A and F with B. This will now allow me to calculate the probability of E and F, which is a little bit hard to do. But I can calculate these other two rather easily. What is the probability of the first card being red? This one here is 1/2, right? Because there's an equal number of red and black cards in a deck of cards. So that probability of the first card being red is easy to calculate. All the cards are there. The probability that a red card is on top is 1/2. Now, this one is actually, this usually we think of as being complicated to compute, but in this case it's not that complicated because there are 26 black cards remaining and there are 51 cards total left. So this is 26 out of 51. If we know we pick a red card first, if we condition on picking a red card first, the probability of a black card is 26 out of 51. Because there are 26 black cards remaining, half of the cards are black, and there are 51 total cards remaining because we've taken the first card and it happened to be red. So those two probabilities I'm able to compute, and that allows me to use the conditional probability formula to figure out the probability that the first card is red and the second card is black, and that turns out to be 13 out of 51, which is slightly higher than 25%. Right? That's slightly higher than 25% because once we know the first card is red, it's more likely for the second card to be black than to be red. So this is a little bit bigger than 1/4. Questions? Okay, now let's change this problem a little bit. Let's change this, let's have another event called G, that is the second card is red. What are the probabilities that the first two cards are red? Well, this is going to be the probability of F and G, which is going to be the probability of G given F times the probability of F again. I should have probably written this G and F to be similar to the way this one is written. Okay, the probability that the first card is red is 1/2 again, so the probability of F is 1/2. Now the probability that the second card is red, given that the first card is red, is now 25 over 51. Because we have taken away one red card, there's only 25 red cards remaining, and there's 51 total cards. So we get 25 over 51, which is slightly less than 1/2, right? Because 25 over 50 would be 1/2. Now when we multiply these together, we get 25 over 102, which is less than 1/4. So it's more likely that the first card is red and the second card is black than the first card is red and the second card is red. Makes a little bit of sense if you think about it. But now we can specify precisely how much more likely it is. Okay, now let's do another problem about two things happening. We're going to roll two dice, one after the other. So we're not rolling them at the same time. We're going to roll a die. We'll have die number 1 and die number 2. And we want to find the probability that the first roll is a 6 and the second roll is a 3. So let's call first row being a 6A, and B will be the event second roll is 3. So those are the two events. We want to calculate the probability of A and B. The first roll is a 6 and the second roll is a 3. And using the formula from above, right, we could say, okay, what is the probability that the second roll is a 3 given the first roll is a 6 times the probability of the first roll is a 6. We could use that formula to calculate those probabilities. All right, what is the probability of A? What is the probability that the first roll is a 6? That is 1/6, right? There's a 6, we're assuming a 6-sided die, right? So that should be 1/6. Now, given that we got a 6 on the first roll, what is the probability that the second roll is a 3? 1/6, right? Does the second die care about the first die? No. Right? All the possibilities are equally likely. This is different from selecting 2 cards from a deck. So this is equal to 1 out of 36. So this is a slightly different situation, and this situation is different enough that it's given a name. And note that this is the same as probability of B times probability of A. Right? Because probability of B given A in this instance was the same as probability of B. When this happens, it's given a special name, and this is this definition here. We say two events are independent if the probability of E and F is equal to the probability of E times the probability of F. We just multiply the two probabilities to find the probability of the joint event. This is called independent. And we could have the same definition would say the probability of E given F is equal to the probability of E. Right? The conditioning doesn't do anything. So when events are independent, conditioning doesn't do anything. Okay. So independence is an excellent concept in the way that it allows you to compute complicated things quickly, as long as those complicated things have nothing to do with each other, right? As long as they can't possibly affect each other, right? So we could say that the probability of it raining tomorrow in St. Louis and the probability of the oil price going down tomorrow, those are probably independent. We wouldn't affect that one thing to have a big effect on the other thing. So if things don't seem to affect each other, we call them independent. And a lot of what we do, a lot of what prognosticators try to do is they're assuming independence because it allows them to calculate things. But sometimes there are hidden dependencies that we hadn't really thought about. And that's where we can sometimes make mistakes when we're gauging likelihood or gauging risk in things. We might miss some hidden things, we might assume two events are independent where there might be some sort of connection between them. So let's do an example where we try to investigate whether something is independent or not. Okay, here's an example. A family has 4 children. Let's have 2 events. E is the event of they have at least one boy, and F is that they have at least one child of each gender. Okay. So they have at least one boy is one event, and they have at least one child of each gender is the other event. So the question is, are E and F independent? Does knowing that a family have at least one boy not change the probability that they'll have a child of at least one gender? Or does knowing that they have a child of at least one of each gender, does that have anything to do with them having at least one boy? Well, that second one is certainly true, right? If we were to calculate the probability of them having at least one boy, given that they have at least one child of each gender, what is that equal to? The probability that they have a boy given that they have at least one child of each gender. Exactly. That's 1. And 1 is probably not equal to the probability of having at least one boy. So looking at this, we see that these are not going to be independent events. So the answer is not independent. How could we figure this out otherwise? Well, we could write down all the possibilities. Right? We have 4 children, and we could have 4 boys, 3 boys and a girl, 2 boys and 2 girls, 1 boy and 3 girls, and all girls. Those are the possibilities when you have 4 children for the distribution. We don't actually care about birth order here. That's not what we're asking about here. And so each of these have likelihood 1/5. Okay. Now, if we try to calculate the probability of E, that would be having at least one boy. That would be all of these together. So this would be the first one, the second one, the third one, and the fourth one all together. So this would be 4/5. So the probability of having at least one boy is 4/5. The probability of having at least one child of each gender, however, is 3/5, because we see that's only these middle ones. So it's indeed more likely that you'll have at least one boy than that you would have at least one child of each gender. And if we calculated the probability of E and F, okay, so this one is E, this one is F. E and F, however, which one of these are true? Where we have at least one boy and at least one child of each gender. That would be this one, at least one boy, and at least one child of each gender. That would be this one, and that would be this one. Okay. So this is equal to 3/5 as well. And now we see that the probability of E and F is not the same as the probability of E times the probability of F. And so we see again that these are not independent events. Okay? So you might be given questions where you're asked, are these two things independent? And you have to kind of do these calculations and figure out whether this is true. Okay. Another example. Toss a coin 3 times and record the sequence of heads and tails, obviously. If E is the event at most 1 head and F is the event both heads and tails occur, then we can ask ourselves, are these events independent? Okay. So let's write down the possibilities here. We have head, 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 tails, head, tails, head, tails, head, head, tails, tails, head, tails, head, tails, head, tails, 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 tails. We should have 8 possibilities, and we have 8 possibilities there. And let's color code these by the event. Let's say at most 1 head is the event E. So that's going to be E is this, 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 and this. At most 1 head is the blue event. Both heads and tails occur is going to be the red event. Okay, so that's where we have both heads and tails. And let's say E and F, having at most 1 head and both heads and tails occur, is going to be yellow. So that's going to be this one. Nope. That's wrong. Okay. Heads and tails. Nope. That's too many heads. Okay. At most 1 head and both heads and tails occur. Okay. So now we've got those all labeled. So I can see now that the probability of E is 5 out of 8. The probability of F is 6 out of 8. And the probability of E and F is going to be 3 out of 8. And the question is 3 out of 8 equal to 5 out of 8 times 6 out of 8? If it is, then those events are independent. Because independence means the probability of E and F is equal to the probability of E times the probability of F. Is this true? Well, this gives us 30 over 64. Okay, and this gives us 15 out of 32. And that is where we stop. Those are not equal, right? This is not equal. So these are not independent. Okay. Even though each successive coin flip is independent of the previous one, various events relating to them may not be independent. Jeff?
The highest blue dot has 2 heads.
Oh, did I make a mistake here? Okay, so I messed this up. Okay, let's see here. So this dot should not be there. You're arguing? That is correct. At most 1. Okay, so now this changes some of our probabilities, right? So this changes this to 4/8. Okay, so that changes this into 24 out of 64, and that is indeed 3/8. Okay, so these are independent. Thank you. I thought this example was supposed to be independent, and I was getting not independent, so good eye there, Jack. He noticed that the first one that I put the blue dot on is not blue because there's 2 heads. We can have at most 1 head. So the events of having at most 1 head and the event of having both heads and tails occur happen to be independent. You might not think they're independent, but we just did the calculation to show that they are independent. So sometimes the independence is obvious, right? If you roll one die and then roll another die and then roll another die, each of those die rolls are independent. What you get on each one is independent of what you get on the previous ones. But if you make a complicated event out of a series of things which are independent, like we've just done here, the coin flips, you might get events which are independent, you might get events which are not independent, depending on the situation. And so you have to kind of count and use the formula to find out what's going on. Okay. So in class, if you can spend some time working on problems 15 and 16, and the homework for today is problems 18, 20, 22, 24, 28, 52, 56, and 64. All right, so I will have the book up here.